Good day, I am Queen Sharma Silverhall from the College of Accounting Education, and I am taking up Bachelor of Science in Accountancy. In this video, I'm going to discuss about multiplicative inverses in modular arithmetic. I am going to explain what multiplicative inverses are and how to find multiplicative inverse. So what is multiplicative inverse? If a product of two real numbers is 1, then the numbers are multiplicative inverse of each other because in the modular arithmetic, the multiplicative inverse of a number is another number that when you multiply together gives a specific result. In modular arithmetic, we are working with numbers that are defined with respect to a particular modulus. A modulus is a positive integers that defines the clock we are working with. For example, we are working with modular arithmetic, modulo 7. We are working with the numbers that defined with respect to the clock that repeats every 7 units. In this case, the numbers that we are working are 0, 1, 2, 3, 4, 5, and 6. In modular arithmetic, we can add, subtract, and multiply just like we do in a regular arithmetic. However, division works a little differently. In a particular, we cannot divide one number by another just to get the whole number quotient. For example, we are working with modular arithmetic, modulo 7. We cannot add 2 by 3 to get a whole number quotient. However, we can still find a multiplicative inverse of a number, which is the number that we can multiply by to get 1. For example, in modular arithmetic, modulo 7, the multiplicative inverse of 3 is 5. It's because 3 times 5 equals 15, and 15 divided by 7 is equal to 2 and has a remainder of 1. In this case, we can also say that 5 is the reciprocal of 3. The multiplicative inverse is an important property of modular arithmetic, and it has a lot of application in the number theory, cryptography, and computer science. A number A has a multiplicative inverse modulo M. If there is a number B, such as A times B, 1 modulo M. In other words, B is the number that we can multiply A by to get 1 when we are working with modular arithmetic modulo M. If A does not have a multiplicative inverse, we can say that A is not invertible modulo M. The existence of multiplicative inverse depends on the properties of modulus M. In particular, number A has a multiplicative inverse only if JCD AM is equals to 1. This means that A and M has no common factors except for 1. For example, when we are working with modular arithmetic modulo 7, the numbers that have a multiplicative inverses are 1, 2, 3, 4, 5, and 6. Because these are the numbers that have no common factors with 7 except 1. To find the multiplicative inverses of a number of modulo M, we can use the Euclidean algorithm. This is the generalization of Euclidean algorithm that we use to find the greatest common divisor of two numbers. The Euclidean algorithm allows us not only to find the greatest common divisor, but also the coefficient of a linear combination that gives us the greatest common divisor. If we apply extended Euclidean algorithm, we can find the coefficients of x and y of a linear combination. Ax plus ny is equals to JCD AM. If JCD AM is equals to 1, then we can rearrange the equation to get Ax 1 modulo M, which means that x is the multiplicative inverse of modulo M. For example, Let's find the multiplicative number of 3 modulo 7. We start by writing down the two numbers as a linear combination of each other. 7 equals 2 times 3 plus 1. Then we work backwards to find the coefficient of a linear combination. So it will be 1 equals 7 minus 2 times 3. Now we can rearrange the equation to get 3 times negative 2, 1 modulo 7. Which means that multiplicative inverse of 3 modulo 7 is 2, 5 modulo 7. Multiplicative inverse have many applications in number theory, cryptography, and computer science. For example, in number theory, they are used to solve the Diophantine equations, which are equations that involve integer solutions. Multiplicative inverses are also used in Chinese remainder theorem, which is a method for solving system of a linear congruences. In cryptography, they are used in the RSA algorithm, which is a method for encrypting and decrypting messages. In computer science, they are used in hashing algorithm, which are used to map data to fixed size output. Multiplicative inverses are an important concept of modular arithmetic. They allow us to divide numbers in modular arithmetic, even when we cannot divide numbers in regular arithmetic. The existence of multiplicative inverses depends on the properties of modulus, and they can be found using extended Euclidean algorithm. The Euclidean algorithm is a method for finding the greatest common divisor GCD of two integers. The GCD is the largest positive integers that divide both of them without leaving a remainder. For example, the GCD of 12 and 18 is 6 because 6 divides both of them without leaving a remainder, and no larger integer has this property. The Euclidean algorithm is based on the fact that GCD of two integers won't change if we subtract one from the other. We can keep subtracting multiples of one integers from the other until we get two smaller integers that have the same GCD. Then we'll repeat the process until we get two integers that have the same GCD. The GCD of the original two integers is the product of all factors that we use to reduce the integers to 1. In solving the multiplicative inverses, we need to find a number that can be multiplied by the given number and produces a congruence of 1 modulo the modulus. This means that we are looking for a number that when we multiplied it by the given number and divided by the modulus, leaves a remainder of 1. One way to solve for the multiplicative inverses is to use the extended Euclidean algorithm. The extended Euclidean algorithm is a generation of Euclidean algorithm that allows us to find the GCD of two integers and also the coefficients of linear combinations that give us GCD. Now let me show you the 10 examples of multiplicative inverses. First example, solve for 7x congruent 1 modulo 11. The inverse of 7 is 8. Multiplying both sides by 8 gives x congruent to 8 modulo 11. Second example, find the inverse of 3 modulo 13. The inverse of 3 modulo 13 is 9. Multiplying 3 by 9 gives 27, which is congruent to 1 modulo 13. Third example is compute the inverse of 15 modulo 26. The inverse of 15 modulo 26 is 7. Multiplying 15 by 7 gives 105, which is congruent to 1 modulo 26. Fourth example, find the smallest positive integer x such that 27x congruent to 1 modulo 37. The inverse of 27 modulo 37 is 14. Multiplying 27 by 14 gives 378, which is congruent to 1 modulo 37. Fifth example, solve for x. 5x congruent to 1 modulo 9. The inverse of 5 modulo 9 is 2. Multiplying 5 by 2 gives 10, which is congruent to 1 modulo 9. Sixth example, compute for the inverse of 17 modulo 23. The inverse of 17 modulo 23 is 5. Multiplying 17 by 5 is equals to 85, which is congruent to 1 and modulo 23. Seventh example, find the inverse of 9 modulo 19. The inverse of 9 modulo 19 is 17. Multiplying 9 by 17 gives 153, which is congruent to 1 modulo 19. Eighth example, solve for x. 11x congruent to 1 modulo 16. The inverse of 11 modulo 16 is 3. Multiplying 11 by 3 gives 33, which is congruent to 1 modulo 16. Ninth example, compute the inverse of 14 modulo 29. The inverse of 14 modulo 29 is 15. Multiplying 14 by 15 gives 210, which is congruent to 1 modulo 29. And the last example, find the smallest positive integer x such that 19x congruent to 1 modulo 31. The inverse of 19 modulo 31 is 24. Multiplying 19 by 24 gives 456, which is congruent to 1 modulo 31.